the mathematicians of ancient Greece had their fingers, the sand, and an invention called the Salamis tablet to do calculations, starting around 300 BC. Well, in 500 AD, it evolved into the Roman handheld abacus. Yet the Greeks, the Romans, and the Chinese, who actually developed the abacus that is still around today, did not have a graphing tool. Fortunately for us, we have graphing calculators, and they have changed the very nature of the way that we study mathematics. Hi, my name is Tom Atwater, and today we are going to investigate solving graphically, algebraically, and numerically quadratic equations. Let's start by solving an equation using the graphing calculator. Solve the equation 2x squared minus 3x minus 2 is equal to 0 graphically and then algebraically. Well, to do this graphically, what you need to know is you want to set this equation essentially equal to y, because that's what we're going to have to do when we enter it into the graphing calculator. In other words, we're going to write y equals 2x squared minus 3x minus 2. And that's what we enter into the grapher using the y key. You would enter in this part of the equation. And if you do that, then you'll end up with the following graph when you press the graph key. And the graph would be this particular parabola. Now, how did I find the 0 is equaling here as equaling x equals to 2? Well, what you have to realize is if we're trying to solve that equation, we're looking for, because we set it equal to y, we're looking for where y equals 0. In other words, we're looking at the x-axis. And you can see right here, the graph crosses the x-axis, and it's very easy to read that. It's right at the point 2. So we know that one of the solutions to the original equation is x equals 2. Well, what about this other one that's over here? That one, we could guess that it's equal to -1/2 because that's what it looks like, or what you could use is the trace function on your calculator. And the trace function on your calculator would yield this graph right here. And the trace function you use by hitting the key that says second and then the key that says calculate, and it actually traces it. And what you find then is we were correct in saying that the other x-intercept, that is where y is equal to 0, is equal to -1/2. So using the graphing calculator, we found the solutions x equals 2 and x equals -1/2. Well, let's look at this algebraically now. That is to say, let's solve this equation by hand. We have 2x squared minus 3x minus 2 is equal to 0. And the method that we're going to use is to factor this left-hand side. And we're going to factor it into two binomials. So what we have then is that this is going to be 2x. This is going to be x. And then, again, we have to break up the 2. I'm going to try +1 and -2. And we'll see that when I do that, the middle terms are going to be +1x and -4x, which when added together gives me my -3x. So those are the correct factors. Now, looking at this equation, what you have to realize is if I have two binomials, two factors here that when I multiply, they equal 0. That means one of them has to be 0, because that's the only way that something times something would equal 0. In other words, 2x plus 1 has to be 0, or x minus 2 has to be equal to 0. In this case, when we solve it, we get x equals -1/2, and over here, we get x equals 2. Which, of course, is what we expected because that's what we found through the use of the grapher that the solutions to the equation were 2 and -1/2. So 2 different methods of finding the same answer. Now, in this example, we used a very important property called the zero factor property. If you let A and B be real numbers, and if A times B is equal to 0, then either A is equal to 0 or B is equal to 0. Well, now it's time for you to try a problem. And I would like you to solve the equation x squared minus x minus 20 is equal to 0 algebraically. So pause the video while you work on this problem, and when you're finished, restart the video to check your solution. All right, let's find out how you did on this problem. You need to factor x squared minus x minus 20 is equal to 0. So to do that, we would factor it as x minus 5 times x plus 4. And now use the zero factor property to say that either x minus 5 has to be 0 or x plus 4 has to be equal to 0. And that means that x is equal to 5 or x is equal to -4. All right, so let's examine quadratic equations now in a little bit more detail. First of all, let's talk about what a quadratic equation in x is. It's one that can be written in the form ax squared plus bx plus c is equal to 0, where a, b, and c are real numbers, and a does not equal 0. Now, of course, why does a not equal 0? Because if a were equal to 0, 0 times the x squared here would cancel out, and we'd be left with what's called a linear equation. So that's why a can't equal 0. Let's do an example of a quadratic equation. Solve algebraically 3 times the quantity x plus 4 squared equals 8. First, what I want to remind you is that what we're doing in this particular equation is using the concept, if we have x squared is equal to 4, we can solve that by taking the square root of both sides. And that would give me answers of x equals plus or minus 2. To do that with our equation, we need to divide both sides by 3. That would give me x plus 4 quantity squared is equal to 8/3. Then I want to take the square root of both sides. On the left-hand side, the square root of x plus 4 squared is just x plus 4. Then I have plus or minus the square root of 8/3. I need to simplify the square root of 8/3 a little bit, so let me pull that over here and remind you that the square root of 8/3 can be rewritten as the square root of 8 over the square root of 3. Then on the top, that would be the 2 square roots of 2, because that's what the square root of 8 simplifies to. On the bottom, we still have the square root of 3. If I then rationalize the denominator, I would have that this equals 2 square roots of 6 all over 3. And that's what this square root of 8/3 is equal to. So therefore, I want to subtract 4 from both sides so that I get my x, and x will then equal -4 plus or minus 2 square roots of 6 all over 3. And of course, that leads to 2 answers, one which is -4 plus 2 square roots of 6 over 3, and the other one is -4 minus 2 square roots of 6 all over 3. So that's an example of solving a quadratic equation using the concept that you can take the square root of both sides. Now let's look at something called completing the square. To solve the equation x squared plus bx equals c by completing the square, you add the quantity b divided by 2 squared to both sides of the equation, and then factor the left side of the new equation. Specifically, if you have x squared plus bx, then we're going to add to that b divided by 2 squared equals c plus the quantity b divided by 2 squared. What that would then simplify to, of course, over here we get b squared over 4, but on the left side we factor it, and it becomes x plus b over 2 quantity squared. At that point, you can then pick up where we just did the previous example, which is you can take the square root of both sides. Let's work an example of this so you can see it in action. Let's take the problem solved by completing the square for x squared minus 20x plus 17 is equal to 0. All right, to do this problem, the first thing is we must divide by 4 so that we have a coefficient on x squared which is equal to 1. So 4 divided by 4 gives me 1x squared. Then I have minus 5x. And then I have the plus 17 fourths, which I'm going to subtract from each side to give me negative 17 fourths on the right, because of course 0 divided by 4 is 0. Now what we can do is take the b term, which is negative 5, divide it by 2, square it, and add it to both sides. In other words, we would have x squared minus 5x plus negative 5 divided by 2 squared equals negative 17 fourths plus the same exact term, negative 5 divided by 2 quantity squared. On the left-hand side, we get x minus 5 halves quantity squared. So that's the factored form that we were expecting to get. On the right-hand side, we have negative 17 fourths plus. When we square this, we get 25 over 4. And then negative 17 plus 25 is equal to 8. But then 8 over 4 is, of course, 2. So what we have then is x minus 5 quantity squared is equal to 2. So let me rewrite that to give myself enough room to finish this problem. X minus 5 halves squared is equal to 2. Now we take the square root of each side, so we will get x minus 5 halves equals plus or minus the square root of 2. Then we have to add 5 halves to each side, so x would equal 5 halves plus or minus the square root of 2. So my two answers are 5 halves plus the square root of 2 and 5 halves minus the square root of 2. So that's an example of where we used completing the square. We can actually formalize this procedure into something called the quadratic formula. The solutions of the quadratic equation, ax squared plus bx plus c is equal to 0, where a doesn't equal 0, are given by the quadratic formula, which is x equals negative b plus or minus the square root of the quantity b squared minus 4ac, all of that divided by 2 times a. I think the best thing to do is an example of where we use this formula. So let's solve the equation using the quadratic formula, and the equation is x squared plus 8x minus 2 is equal to 0. So what we have here is that a equals 1, b equals 8, and c equals negative 2. We just need to plug those numbers into the quadratic formula, so let's do that on the next slide. And what we would have is that x is equal to negative b plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is negative 2. And that's all over 2 times a, which is 2 times 1. If we simplify this, we get x equals negative 8 plus or minus. Well, underneath here, 8 squared is 64. Then we multiply the 4 times the 1 times the negative 2, and that's actually, including the negative here, would become plus 8, which means underneath there we have the square root of 72. And that's all over 2. Now, the square root of 72, you should recognize that that's really 2 times 36. So we can simplify that to x equals negative 8 plus or minus. We can take the 6 from underneath there, leaves us with the square root of 2. That's all over 2. But now we'll notice that we can reduce these down. The 2 goes into the 6 and the 2 goes into the 8. Leaves us 3 there and 4 here. So we get the answer negative 4 plus or minus 3 square roots of 2. And of course, that gives us our two answers, negative 4 plus 3 square roots of 2 and negative 4 minus 3 square roots of 2. Okay, let's summarize where we are so far. There are 4 basic methods that we've used to solve quadratic equations algebraically, and they are this. Number 1, we used factoring, and we used the zero factor property. We used number 2, extracting square roots. That was the example where I started off with x squared was equal to 4, so x was equal to plus or minus 2. Then we did completing the square, and then finally, in the last example, we used the quadratic formula. One of the things that happens with quadratic equations is sometimes you get approximate solutions and not exact solutions, especially when we do them with a grapher. So we're going to use the following agreement in this textbook. And the agreement is, for applications, round to the value that is reasonable for the context of the problem. Whereas for all other problems, round to 2 decimal places unless otherwise directed. So that'll give us a method that we'll all come up with either a 2 decimal answer, or in particular, if it's a word problem, we put it in the context of the word problem. Now, sometimes we can rewrite an equation and solve it graphically by finding the points of intersection of 2 different graphs. For example, a point A comma B is the point of intersection of 2 graphs if that point A comma B lies on both graphs. So let's do an example. Solve the equation, the absolute value of t minus 8 is equal to 2, graphically by finding the intersection of what would be the 2 curves. The 2 curves are y equals the absolute value of t minus 8. The second curve is y equals 2. So we would enter each of these equations into the grapher using the y key, and then we would have to enter a second equation using the y key of 2, and then what will happen is the grapher will graph those 2, and we will end up with looking at the intersection of them. Well, the absolute value, remember, is a V-shaped graph, whereas y equals 2 is a horizontal line. So we'll be looking at right now the intersection of a horizontal line with a V-shaped graph, and this is what we get. We have the point of intersection right here of x equals 6. And I'm looking down here to see that's a 6, but also I suppose I could look at the x-axis to see that. So there's my V-shaped curve giving me the answer x equals 6, which means if I stick 6 into here, of course, 6 minus 8 is -2, but the absolute value of -2 is 2. Well, what about this other point? Let's take a look at the grapher finding that point for us. And you'll see that this time x is equal to 10. And again, plugging it in, 10 minus 8 is 2. The absolute value of 2 is 2. So we can see, checking it algebraically, that the graphing calculator gave us the two answers, x equals 6 or x is equal to 10, and we didn't have to do that algebraically. All right, great work in today's lesson. So in this section, we explored solving quadratic equations algebraically and graphically. Be sure to work the exercises that your teacher assigns, and we'll see you next time.